Okay, welcome. Very excited to be here. This is my first PyCon Israel. And welcome to Pandas for Fun and Profit. So let's start with a question. How many of you, let's say in the past year, how many of you have had to make a decision about what to do with your money? Raise your hand. Quite a number of people. Okay, next question. How many of you used data science and data and math to figure out what to do with your money? A little bit less. Okay. So that's what we're going to talk about today, but the gist is this is really about Pandas. This is a beginner class or a beginner talk, the basics of Pandas, by way of example, using an example that I think you might find interesting, that I found interesting, looking at a little bit about stock investing. So what is Pandas? Pandas is a Python-based data analysis toolkit. Provides high-performance, easy-to-use data structures and data analysis tools. It's built on top of NumPy, so it takes advantage of some of the things that NumPy has, and it also uses Matplotlib under the hood for visualization. So here's the backstory. I only started using Python about 7 or 8 months ago. A few months ago, I heard about Pandas. I got very excited. It sounded interesting. I took a 3-hour online workshop about Pandas from Matt Harrison. And I said to myself, wow, this is really cool. I want to learn more about Pandas. Maybe I can use this to test some ideas that I have in the marketplace. So I decided to take this project that I had in mind and just do it in Pandas so that I could learn more. So a little bit about me. I'm an engineer at Bloomberg. I spent most of my career doing C and C++ on the server side. I was a member of the Chartered Financial Analyst Institute for 10 years. And I started my career a long time ago in biophysics. A little bit about Bloomberg. We provide all of these services to several 100,000 financial market professionals. And we also provide to the public financial news via television, radio, and online. We have about 20,000 employees in 167 locations worldwide, including Tel Aviv and Jerusalem. We have over 5,500 software engineers, and more than 2,000 of them are involved with Python. So in conclusion, actually I just decided that to do something different in this talk, I'm going to give my conclusions at the beginning so you'll have what to think about as I go through the talk. So the conclusions are Pandas makes it easy to explore your data, to shape your data, to analyze it, and visualize it. However, as powerful as Pandas is, it's important to know your domain, have some domain knowledge. You don't necessarily have to be an expert. You have to have some domain knowledge about your data. And you should also plan to spend 50% or more of your time shaping your data. That is, getting it into the data structures that are most suitable for the analysis that you want to do. And therefore, about 50% of this talk or more will be about shaping the data. So let's talk about stock ownership. When you buy a stock, you actually own part of the company. And what's a company? A company is nothing more than a group of people working together to earn money. And earning money has value. So for that reason, a lot of people look at what's called the price-earnings ratio. That's the price of the stock divided by the earnings of the company. And there's a concept that if the price-earnings ratio of one stock is less than that of another stock, then the stock that has the smaller price-earnings ratio, you're getting more for your money. That stock is said to be underpriced. So before we can test this hypothesis that a low PE is actually underpriced or a bargain, let's talk about Pandas. So there's 3 primary data structures to understand Pandas. There's the index or multi-index, a series, and a data frame. An index is nothing more than a list of keys that point to data. It's essentially a hash table. You can think of it as a Python dictionary. A series is the data combined with the index. So you have a list of data, and you have the index keys pointing to that data. Here's an example of a series. We have the values here. Here's the index. In this case, the index is our date objects, the index name, the name of the series, and the data type of the series. Those are the basic parts of a series object. So what can you do with the series? You can take the len of the series, see how much data you have in there. You can access the data either by key or by position. Here's an example of accessing the data by key. We put in a certain date, we get back the data for that date, or by position. So let's talk about a data frame. A data frame is a two-dimensional spreadsheet. You have your rows and your columns. Each column is a Pandas series, and each row is a Pandas series. Here's the parts of the data frame. We have the same things, the values, the index name, and now we have columns. Notice if you take a look at the index attribute on the data frame, we see an index object which contains the list of keys. The columns attribute is also an index object. This is important to understand, that both your columns and your index are index objects. This hash table that points to the data. The only thing is, on the horizontal axis we call it columns, on the vertical axis we call it index, but they're both indexes. So here's some things you can do with an index. You can take the shape, see how many rows and columns you have. Again, you can access the data by key. However, in this case, since we have two indexes, you can do both rows and columns in your key to get a particular data element. You can also use just a row or just a column. Here's an example of using just a row. So when I pull out a row, as I said before, a row is a Pandas series. Notice that when I pull out the row and I get a series, the index on the series are actually the column indexes on the data frame. And the name of the series is the key for that row that was pointing to the series. Here's a multi-index. A multi-index, basically you have multiple levels of indices. You have a level 0 index, and those keys point to a level 1 index. You can have more than that. In this case, we actually have 3 dimensions because we have 2 indices on the columns and 1 index on the vertical axis. You can have as many indices, as many levels as you want, so that you can basically express in 2 dimensions as many, express in 2 dimensions as many dimensions as you want. All right, so now we know the basics of Pandas. So now we can test our hypothesis, which was that low PE represents a bargain, and if so, then buying stocks with a low PE should result in higher returns. So we have to somehow compare the PE to returns, and we want to see a negative correlation. We want to see when the PE goes down, the returns go up. So this is the fine print. This is information, not advice, yada, yada, yada. Okay, so we need a data set to test this. I chose for my data set the 30 stocks in the Dow Jones Industrial Average. I would have much preferred a much larger data set, the S&P 500 or the Russell 5000. However, this was my first time using Pandas. I wanted something small that I could actually scroll around the data frame and see all the data to understand what's going on. We're going to need the price and the price-earnings ratio for these stocks, and we're also going to need to calculate the return, which means we need the prices and the dividends for these stocks. So I got myself a CSV file of the price-earnings ratios. It's kind of ugly, but Pandas has a very handy read CSV method, which you can call, giving it the file name, and it takes that CSV file and it puts it into a data frame. Now notice when you read it plain, it simply creates an index and column headings that are numeric. But now you can look around the data frame and see what you got. You can see here in the upper left-hand corner, we have the start and end date for the entire data set. We have a lot of nans where there's no data. In the third row, I can see the ticker symbols for the stocks. And in the first column, I can see the dates. I can see also that rows 4 and 5 are just telling me the field that I requested, the price-earnings ratio, so I don't need that. So I can call read CSV again, and now I can specify the header row is row 3, index column is column 0, parse dates equals true means if you see something that looks and smells like a date, turn it into a date object, and I'm telling it to skip rows 4 and 5. Now I have a better looking data frame. I have my ticker symbols as the column headings, dates along the index. But I'm still not happy with this because I don't want to have to type in this whole long string for each ticker every time I want to access a column by date. All I really care about is the ticker itself. I don't need to know these 2-letter codes are the primary exchange that the stock trades on, and the word equity just tells me that it's a stock. So if I look at the index, I see it's just a list of strings. I can use a list comprehension and split out the first token. And then I have a better looking data frame where now I can access the data frame simply by the ticker symbol of the stock and the columns and the dates on the side. Notice, however, that I have a lot of missing data back in 1989. Some of these stocks didn't exist then or weren't trading back then, or they didn't have earnings to report a price-earning ratio. I also have 31 columns. What's going on here? I got 30 stocks from the Dow Jones Industrials. So again, I was able to look through my data frame and I discovered that I had an extra column. It was the index itself, the Dow Jones Industrial Index. Fortunately, data frame has a handy method called drop where I can tell it to drop any number of columns or rows. So here I'm telling it to drop the column that includes the Dow Jones Industrial Index, and now I'm down to the 30 stocks. This is just me, again, exploring the data. Pandas allows you to explore your data, and I personally like to do that a lot before I do analysis, poke around, see what it looks like. So here I'm looking at the end of the data frame, and I see I have a lot of data there. And looking through the data frame, I noticed that most of the missing data was in the older dates. The shape of the data frame was 360 by 30. That's 30 years of monthly data. I don't really need that much, so I decided to take the last 144 points, the last 12 years of data, and now I have data beginning in 2007, and there are no missing points, at least as far as I can see there. So now the data, this is just me, again, exploring the data. The shape is 144 rows. I checked the type of some of the cells to make sure that the types were converted. Read CSV will attempt to convert it to the proper type, but if there's any stray characters in your CSV file, it might leave everything as strings, and there are methods where you can convert it manually yourself after cleaning up the stray characters. So let's describe the data frame. Data frame has a method called describe, which goes through column by column and gives you the count, the average, the standard deviation, min and max, and the various quartiles of the data. It's another way to look at your data, see what's going on. And each of those attributes also has a method of its own. Here I'm calling count, and it gives me back a series which contains the count for every column. And then I notice that one of the columns only has 25 data points. I can compare the series count with the scalar, 144, and I get back a Boolean series, which tells me true or false whether or not the count is less than 144. And now here's the nice thing. I can then take that Boolean series and filter out the columns that have less than 144 data points. That gives me a list of 3 stocks that had less than 144 data points, and I can call drop on that and get rid of those stocks. So now I'm down to 27 stocks, but at least I know I have data for everything, so I'm not going to worry how that's going to affect my analysis. So taking a look at the mean, you can call mean and get a series. And the nice thing about every series and every data frame is that it has a method called plot, so that you can plot the elements of the series in the data frame. If I plot the mean, I get a nice colorful graph with the stocks along the bottom. Everything looks good. There's nothing really standing out a whole lot. There's a couple of stocks that are kind of high. They're a little more expensive. But if I look at the standard deviation, whoa, there's one stock there that's standing out way more than the others. So I wanted to see what was going on with this stock. So I plotted the PE ratio over time for that stock, and I see back in 2017, this stock's PE ratio shot through the roof. Now what can happen when companies report their earnings typically quarterly, and occasionally they have a loss and they report negative earnings. That's not what's happening here, because if they do report negative earnings, then we don't calculate a PE ratio. But sometimes they have a loss, but they end up reporting very slightly positive earnings, maybe a few cents. And if that happens and the stock price was already high, the PE ratio is going to go through the roof. So I decided to drop this stock just so it wouldn't affect the analysis. I can always add it back later and see how it does affect the analysis. Now we look at the standard deviation. Everything looks good. No one's really standing out all that much. So how are we going to define a low PE? I've kind of been implying that what really matters is the PE in relation to the other stocks. So I want to say that I want to look at the number of standard deviations that the PE of a given stock is below the market average. And that's what we call the Z-score. So I grabbed the mean and the standard deviation. I put them into a data frame of themselves because I'm going to need those to calculate the Z-score. And I plotted it again. I want to explore my data, see what's going on. It looks kind of normal to me. It's moving around. The standard deviation is less than the mean. That's good. And now I can calculate the z-score. The data frame has methods, subtract, divide, add, that sort of thing. So I can take this way, I can do in a single line of code, I can do math on every element in the entire data frame. So I'm subtracting the mean, dividing by the standard deviation. That gives me the z-score. I see some of them are very positive. These are stocks whose PE is very much above the average. Some are negative, they're below the average. I decided just to look at the max and min of each stock, just to take a look at what it was, if it seemed normal or anything was standing out, and I plotted that. So I have the max and min PE ratio for every stock. Everything looked kind of okay to me here. There was nothing standing out that made me worried. So now we have a way to measure whether the PE is high or low, and we need to calculate returns so that we can compare them. Formula for return, final value divided by starting value. But if I want to compare returns for different periods, because I want 3-month returns, 6-month returns, it's good to annualize the return. The other thing to note here is that the final value requires both the final price and the dividends that were earned during the period of return that we're calculating. So I have a CSV file of prices. I read that in. Same issues as before. I cleaned it up a little bit. This also goes back to 1989. There's a couple of stocks missing prices. They weren't trading yet. So I want to get this data frame into the same shape as the PE ratio data frame. Now I could try to remember which stocks I deleted and which dates I deleted, but a nice handy dandy thing is that I can pull out the start date and end date from the PE ratio data frame, and I can use that to slice the prices data frame, and I can also put the columns from the PE data frame to select out of the pricing data frame, and now I have the pricing data frame the same shape as the PE data frame. Now what about dividends? What shape should the dividends be? It's always good to figure out what shape, what data structure you want your data in before you read it. The issue with dividends is that, well, dividends are money paid to shareholders, and the data is sparse. Some stocks don't even pay dividends. They pay quarterly. Sometimes they don't pay. And what I really need to do is I need to find the dividends, again, during the period that I'm calculating returns. So I decided to store my dividends as a dict, where the key is the ticker symbol and the value is the series of dividends by date. And then I can grab the series as I'm calculating the return for each stock and go in and slice by date those dividends that contribute to the return. So here is my dividend CSV file. It really looks kind of ugly. It turned out, perusing the file, that this isn't actually the file, this is the data frame from the file. Every stock had 9 columns in this file. I have the stock ticker symbol in one column, nothing else in that column, a date column and an amount column, and the other columns I don't need. So I wrote a loop to go through the data frame 9 columns at a time and pull out the stuff that I needed. You can take a look at this later. I won't go through the code now. And I ended up with a dictionary where the keys are the ticker symbol, and I can go in by each ticker symbol and I get a series of the dividends. This is me just testing that my idea works, that I can key into the dividend dictionary by stock and by date range, and then I can sum up the dividends from that series and get the total number of dividends that apply to the return. So now I want to calculate the return for different periods of time because I don't know which ones may or may not correlate to the PE ratio. So this means that for each date, I go to that date, and let's say a 3-month return, I go to the date 3 months later, that's my final price, calculate the dividends, get the dividends from in between there, add it into final price, calculate the return, and then I move to the next date and do the same thing. So there is no method to calculate returns, like there's a mean and standard deviation on a data frame, but there is a method called apply, which allows you to apply any function that you write to the data frame. So I wrote a function to calculate the returns. The important thing to note here is that it passes in the columns, because I'm going column by column. Each time it calls my function, it passes in a column of prices, and I can grab the dividends and calculate them that way. So I called apply. I now have returns. Some are positive, some are negative. This is an example of 3-month returns right here. So how do I know if the return is high and low? Well, just as before, I want to compare it to the marketplace. So I want the z-score for each return. And then we'll take the correlation between the z-score of the PE and the z-score of the return. So here I just plotted it for one stock. Again, I like visualizing things. So I see down here, for example, in 2013, with the z-scores going low, the returns are going higher. This stock's return is 2 to 3 standard deviations above the market. Looks kind of good to me. Picture's worth 1,000 words, but there's strength in numbers. So let's just calculate the correlations. So the series has a method called core, where you can pass in another series, gives you the correlation for that. I wrote myself a function that where I can pass in the range of data points that I want. Here I'm doing the entire 144-month correlation. And I correlated against all 5 return periods that I calculated, 26 stocks, that's 130 returns. And I found that the mean correlation is negative, but only slightly. So now I'm getting a little nervous. Maybe my low PE investment strategy is not going to work. Now this is a good thing. This is the whole point of this. If you run the numbers and it says it's not going to work, save your money, right? It's telling you that if it didn't work in the past, it's probably not going to work in the future. So I poked around on the data some more. I looked at some of the positive correlations, which is not what I was hoping to see. I also looked at some of the negative correlations, and I noticed that in general, those stocks that did show negative correlations were correlating with the longer returns. So much for getting rich quick, but there's an idea here. Maybe I can invest in stocks that have low PE and show a negative correlation. So I have, here's my test plan. I have 3 trading strategies. One is buy all the stocks. That's basically just investing in an index mutual fund. Buy the stocks with low PE. That was my original hypothesis. Or buy those with low PE that give a history of negative correlation. So we need a period of time where we calculate the correlation, and we also need a gap to calculate the return. So for example, with a 2-year return, the latest correlation that I can calculate is 2 years before my trade date. Otherwise, I'm using prices in the future of my trade date. And if I could predict the future, I wouldn't need this whole analysis. However, once I set this up, I can then move forward in time and do this for many different dates. So I ran this for every date from January 2014 to January 2017. That's 36 months, doing all 3 trading strategies as if I was buying the stock, holding it for 2 years, and selling it each month. So this is just 6 of those months, showing you that you can see here on some of the months, the negative correlation, low PE strategy did a lot worse than the market, and in some cases it did a lot better than the market. But if I take all 36 months together, I notice that at least for the case of 2-year and 3-year correlations, I beat the market by between 2 and almost 4%. Now that's assuming that I have enough money to invest every single month in all those stocks. But if I was only going to invest once, I could look at those 36 months as 36 different scenarios. And if I look at it that way, then the low PE case is about 50-50. Half the time beat the market, half the time not. And the negative correlation low PE case beat the market almost 2/3 of the time and didn't beat the market about 1/3 of the time. So in conclusion, Pandas makes it easy to explore your data, to shape it, analyze it. You need to have some domain knowledge and plan to spend 50% or more of your time shaping your data. Thank you. Question? Okay, so the question was, how well does this work for really large data sets? I'm hoping it works really well. As I said, I wanted to do a large data set, but since this was my first time using Pandas, I did this small. I literally just finished this about 10 days ago. So I'm hoping to try a large data set next, and maybe I can post it somewhere and let you know how it worked out. Okay, thank you.